Hi, my name is Brent Bottles, and this presentation is on thorium, and I would like to discuss why I believe that thorium-232 is a better option than uranium-238 for fuel production in nuclear reactors. Now, thorium presents many benefits over uranium, including the availability and abundance of thorium compared to uranium, nuclear proliferation concerns for weapons production, and the reduced volume and radioactivity of waste in certain applications of thorium-fueled reactors. In the presentation, I'll be focusing on the breeding cycle for creating burnable uranium-233 from thorium-232. I'll go over the benefits of using the thorium breeding cycle over the uranium-238 breeding cycle. We'll talk about why uranium-233 is a more efficient fuel than both uranium-235 and plutonium-239. And I'll be touching on some of the benefits that thorium has over uranium in the fuel processing and manufacturing. Now, thorium, it's number 90 on the periodic table, and it's not a fuel. It can't fission. However, it is considered fertile in the fact that it can produce highly fissionable uranium-233 through a process of neutron capture and 2 subsequent beta decays. The fact that thorium itself can't fission gives it great advantages over some nuclear fuels, and that there are no criticality concerns in handling and processing. Thorium-232 is a naturally occurring isotope with a half-life of 14 billion years, and it accounts for nearly 100% of the naturally occurring thorium found on Earth. This is a great advantage. The one that you want is the one that's there. Now, other isotopes ranging from thorium-227 to thorium-234, they have relatively short half-lives in the range of about 25 hours to 75,000 years. So nearly all of the naturally occurring deposits of these two isotopes, or the isotopes available, have long decayed away. Now, being that thorium-232 makes up all of the available thorium, there's no need for an enrichment stage in the manufacturing process, giving thorium a great advantage over other nuclear fuels. Now, in order to create the fissionable uranium-233, thorium-232 will first absorb a slow neutron, creating thorium-233. Thorium-233 has a short half-life of only 22 minutes, and this will quickly beta decay into protactinium-233. A protactinium-233 has a half-life of 27 days, so it takes a little while, but it will eventually decay into uranium-233 through beta decay. Now here we can see the neutron capture chain for thorium, where thorium-232 will absorb a neutron and become thorium-233. The thorium-233 will then in turn go through 2 beta decays, first into protactinium-233, and then another beta decay into uranium-233. Now, once we have the uranium-233, we can start using it for fuel. For the fissile uranium-233 nuclei, the number of neutrons released during fission per neutron absorbed is actually greater than 2 over a wide range of the thermal neutron spectrum, unlike uranium-235 and plutonium-239. This figure shows the neutron yield per neutron absorbed for a couple different fuels. On the left side, you can see the number of neutrons per neutron absorbed and subsequent fission. At the bottom is the incident neutron energies for those neutrons that are being absorbed and causing fission. Plutonium-239 and uranium-235 tend to drop off below 2 neutrons yielded per fission in most of the range of the incident neutron energy spectrum. Towards the right side, where you have higher neutron energies, fast neutrons, you can see why plutonium-239 greatly exceeds the other fuels and starts to go up towards 4 neutrons yielded per fission. However, the benefit of uranium-233 is that it is going to stay above 2 neutrons per fission
throughout the entire spectrum of neutron energies. This means that it's not going to be affected by the type of reactor, be it thermal or fast neutron reactors, and gives a great benefit as a fuel in nuclear reactors.
Now, as we saw in the chart, the uranium-238 to plutonium-239 breed cycle can only be obtained in the fast neutron spectrum. This gives uranium-233 an advantage in that it is less sensitive in the type of reactor, fast or thermal, used for power generation. An additional benefit of uranium-233 producing two neutrons over the wide neutron energy spectrum is that in high-efficiency neutron reactors, there's actually a potential to breed more fuel than is burned. In addition to the production benefits, uranium-233 is a much more efficient fuel with a higher mean fission cross-section than that of uranium-235. And it has a lower mean capture cross-section than that of uranium-235. This lower to capture and fission ratio for uranium-233 relates to a smaller rate of non-fissile absorption and a higher efficiency in heat production.
This table shows the neutrons available for breeding from uranium-235, plutonium-239, and uranium-233. But I can use this table to show the benefits of uranium-233 as a fuel over both uranium-235 and plutonium-239 when it comes to the cross-section for absorption and subsequent fission or capture of neutrons. Now, uranium-235 and uranium-233, if you look at the second row down, the cross-section for absorption and subsequent fission of both of those is basically the same. And plutonium-239 outweighs both of them. But that doesn't matter if you consider the cross-section for absorption and subsequent capture of neutrons. Now, in the thermal range for uranium-235 and uranium-233, the cross-section for capture in uranium-235 is 112 barns, and uranium-233 is half that at 54 barns. So the advantage uranium-233 has over uranium-235 is that when the isotope absorbs a neutron, it's more likely to create fission instead of absorbing the neutron and just subsequently capturing it. And that's shown in numbers by the third row, which is the cross-section for absorption and capture over the cross-section for absorption and fission. You can see that that number in uranium-235 in the thermal neutron range is 0.19, and it's almost half that for uranium-233 at 0.102. Now, when you're talking about uranium-233, this is going to come from a breeder reactor using thorium-232. So it's better for us to look to compare uranium-233 with plutonium-239. And if you do that, the ratio for the cross-section of capture over the cross-section for fission is a third, almost 1/4 that of plutonium-239. The plutonium-239 ratio is 0.375, and the ratio for uranium-233 comes in at 0.102. Now, another advantage that uranium-233 has over the other two fuels is shown on the fourth row, which is the N-1. This is basically after the uranium fissions, one of the neutrons is going to go on to create another fission. This N-1 shows me how many neutrons I have left after that has happened. So in uranium-235, we have just above 1 neutron available. For uranium-233, the N-1 is greater than 1, which is good. The higher N-1, the better. That means you're making more neutrons than you're actually using for the fission process. So you can see on this chart how uranium-233 has benefits in efficiency over plutonium-239 and uranium-235. Now in this figure, if you focus down on the table 3 at the bottom, talking about cross sections, you can see that the cross section for capture of thorium-232 is approximately 3 times greater than that of uranium-238, which is used in the uranium to plutonium breed cycle. This means that thorium has an advantage over the uranium-238 and that it is far more likely to absorb a neutron than the uranium.
Now, in the thorium cycle, a small amount of uranium-232 impurities that will be produced through neutron interactions with protactinium-233 and uranium-233. Now, with the uranium-233, it absorbs a neutron and 2 are expelled, creating uranium-232. In the case of protactinium-233, it does the same. It absorbs a neutron with 2 being expelled, producing protactinium-232. And then this goes through a subsequent decay down into uranium-232. Now, this isotope uranium-232 is undesirable, where it does not fission and it experiences high energy alpha decay with a half-life of over 68 years. Now, the production of uranium-232 can be avoided by separating out the protactinium-233, which is produced with the thorium neutron interaction, and allowing the natural beta decay into uranium-233 to occur.
Now, this chart is a good representation of just how radioactive the uranium-232 isotope can be. It's showing the dose rates at a half a meter from a 5 kilogram sphere of uranium-232 in different concentrations. It's also showing the dose rates for weapons-grade plutonium. And actually, one of the 2 lines that are shown there at the very bottom of the chart, which you can see barely come off the bottom, is actual weapons-grade plutonium. This line that represents just 5 ppm concentration of uranium-232 is actually going up towards 200 milligram per hour, just approximately 5 years after the decay. So you can see how just small concentrations of uranium-232 can have profound effects on the radioactivity of the material. Now, proponents of thorium will see this as a benefit, that anybody wanting to use uranium-233 as weapons-grade material is going to have issues not only with the radioactivity of the material, but that material is also going to be easily detected.
Now, due to thorium not being a fissile material, neutrons must be provided by additional fuel processed with the thorium oxide, or sources added to the reactor core to initiate the thorium-232 to uranium-233 cycle. Because of this, thorium reactors are required to be loaded with a mixed fuel containing either uranium-235 or plutonium-239 to initiate the fission process. Once uranium-233 inventories become adequate for reactor startup, this is a time period referred to as doubling time, there is no longer a need for additional fuels to be added to the reactor for maintaining operations. Now, the doubling time for uranium-233 reactors has the potential to be considerably long, especially in reactors with poor neutron economy. Now, due to the Earth's thorium supplies being nearly 100% thorium-232, there's really no need for an enrichment or separation stage during the thorium processing. This gives it a great advantage over other nuclear fuels with regards to cost and safety. Not only is the enrichment of uranium expensive, the handling of uranium hexafluoride is extremely dangerous. Now, fluorination is a process that will allow the handling of uranium to be done in a gaseous form, which is good for enrichment and separation. Unfortunately, the uranium hexafluoride is very unstable, and it will react with water to form large clouds of hydrofluoric acid. Now, hydrofluoric acid is a caustic and highly corrosive acid that can cause skin, eye, and respiratory damage in relatively low concentrations. Now, reactions to form this hydrofluoric acid can be initiated by just the water in the atmosphere. So handling uranium hexafluoride is very dangerous and involves extensive health and safety precautions. Now, aside from eliminating the health risks associated with handling UF6, eliminating the enrichment stage will take away a large cost as well. A separative work unit is a measurement of the separation done during the enrichment process, and depends on the enrichment of the feed going in and the enrichment of the product and the tails going out. And it takes approximately 62 of these separative work units, referred to as SWU, to produce about 10 kilograms of low enriched uranium from 102 kilograms of naturally occurring feed. So you get an enrichment to 4.5%, and you're only left with 10% of your original feed material. Now, considering the cost of enrichment being around $145 per SWU, and the consumption of low enriched uranium to be about 210 tons over the course of a year, the enrichment cost alone can be in the expense of $17 million annually. And then that's just for one reactor plant. Now, thorium holds another distinct advantage over uranium in the manufacturing process, in that thorium dioxide, THO2, is very stable and it does not go through further oxidized states. Uranium dioxide, on the other hand, the UO2, will readily go through further oxidation into UO3 and U3O8. Now, uranium dioxide is the most desirable for producing high-density ceramics in the manufacturing process, and great efforts are made during conversion and sintering to keep the uranium at that lowest oxide state. Thorium dioxide does have its disadvantages, though, in that the melting point for thorium dioxide is the highest of all oxides at 3,300 degrees Celsius, which means that sintering must be carried out at temperatures over 2,000 degrees, which is more than twice that of uranium dioxide. However, using small amounts of sintering aids like calcium and magnesium oxides can produce high-density pellets in the sintering temperatures as low as 1,150 degrees Celsius. In fact, the addition of around 2% of U3O8 has shown in India to enhance the densification of thorium dioxide, and high-density pellets could be obtained by sintering in air at 1,100 degrees Celsius. Now, this presents an opportunity to produce high-density thorium-uranium oxide fuels without the need for additional oxides, and it gives you your starting fission fuel in uranium-235 to initiate your thorium to uranium-233 breed cycle. So I've gone over a couple of benefits that I see in thorium using the thorium-232 to uranium-233 breed cycle instead of the uranium-238 to plutonium breed cycle. Now, in addition to the ones that I noted, there are several benefits of thorium in its abundance on Earth and the reduced waste in some applications of thorium-fueled reactors. So is thorium a viable option? I think so.